Assalamualaikum warahmatullah.
Waalaikumsalam.
Okay,
Wah, Prof.
we wait for other student to come.
Okay.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon. So, welcome to the new student. A few students add in the list. Okay, can you hear me? Hello? Hello?
Yes, Prof. I can hear.
Yeah, okay.
Yes, Prof, can hear.
Please respond because we are online. So I'm worried you can't hear me. Anyway, it's recorded. Okay, so after finish the class, I will upload the recorded lecture in the YouTube as usual. So in this week, I will review a little bit on the chapter 1 because 2 or 3 students just came in before the chapter 1. So I already sent I think about 2 slides to you. One is the profile slides, which describe on the syllabus, the assessment, and reference book. And then I sent already chapter 1, okay, with the book chapter. And then today I will go to chapter 1A and then 1B. Then today we will finish chapter 1, inshallah, and next week we will go to chapter 2. So I am sorry, last week I'm not feeling well due to heavy rain in Malaysia. Okay, so fall sick, but now I recover. Okay, so let's go to the journey to identifications. Okay, how we going to apply identification to the unknown system from the beginning to the end in the roughly manner, okay, in a brief manner. So the first concept is the identifiability. So we must have the ability to identify a unique model. Okay, unique model meaning uh, the one and only. Okay, is a unique. Okay, we call it as a unique model for a given systems. Actually depend on the 3 critical aspects. Okay, the first thing first is the model. Okay, the property of the model, whether is a one-to-one or exists a unique mapping between the model and the parameters being estimated. Usually parameters is the coefficients, okay, of the transfer function or the coefficients of the matrix and so on. The second one is the experimental conditions. I mean, it is the protocol. Protocol meaning procedure or standard of procedure. What to do first, what to do next, what to do in the middle, and if the target is not achieved, what should we do? Either we redo the experiment and so on. So this will include the input signal, okay, the input signal and the sampling rate that you use, which will give you the most influential and significant design factor. So input must generate the requisite informations required to distinguish between 2 candidate models, which is the real model and the estimated model. Okay, so usually the real model we cannot touch, it is already there, but we never know what is the mathematical model. So that's why we propose estimated model or simulated model, so that it will be the nearest model that match to the real model. And then the third criteria is the estimation method. Okay, so there is a lot of estimation methods. Okay, if you go along the book, go along the journal and conference paper. Okay, so the number of methods must be available, must be established, must be recognized. Okay, so it must estimate the true parameters if infinite samples are available, which is termed as asymptotic property of the estimator, or known as consistency. So asymptotic meaning the nearest, okay, more or less the nearest, okay, the nearest approximations that can fit the real model, okay. So example here, I give you a simple one. Consider fitting the model y bracket, square bracket, k theta, okay, equal to theta 1, theta 2, uk. So this meaning that y is the output, okay. So see, this is the output, okay. And then theta 1 and theta 2 is the parameter that we are going to estimate. U is the input. Okay, So U is the input, and theta 1 and theta 2 is the parameter that we're going to estimate, and then K is the sequence number. Okay, the samples number start from 0, 1, 2, 3, and so on. So to a given data where U and YK are the input and output of a system. Okay, so therefore theta is equal to theta 1, theta 2, square bracket, okay, power of T. T meaning that, okay, T meaning that it's transpose. Okay, so the given matrix here is theta 1, theta 2 transpose, meaning that we have to interchange the row column. Okay, this row column become this row matrix become a column matrix. Okay, so this is row, this is column. That's why if you apply T, it will become a column. And theta 1 and theta 2 is the parameter vector to be identified. Okay, so the solution here is the predictions. Okay, so mainly we have two predictions and the real one. So if predictions, it must have a symbol hat. Okay, so this symbol hat stands for predictions. Okay, if there is no hat, sorry, if there is no hat like this, okay, so this one is considered as a real one. Okay, so Y estimate, okay, K theta is equal to theta 1, theta 2, UK. Okay, U is the input. So regardless of the input, the two different parameters values, which is theta 1 and theta 2, produce identical predictions. Okay, and we can state mathematically as Y cap K theta 1 equal to Y cap K theta 2. Okay, some lectures they give a Y cap, some of them call a Y hat. Hat and cap is the same thing, one American and one British. So since I graduate from British University, we call it is Y hat. Okay, Y hat and hat equal to, therefore theta 1 is equal to theta 2. So therefore the mapping from the parameter space to the model prediction space is not one-to-one. Okay, so formally this model is said to be not identifiable or globally. Consequently, it is not possible to arrive a unique estimate of theta. So on the other hand, if the model is reparameterized, meaning they recalculate again in terms of the single parameters, so we leave it as B is equal to theta 1, theta 2, which is equal to theta 1 and theta 2, then the model is identifiable at all points in the B space manner or in the B space vector. So these examples is shown in the book chapter. You can read the book chapter that I already WhatsApp to you. Okay. So in example 2, we are looking at the linear time invariant system governed by the following input and output relations, okay, which is in the third order finite impulse response. This is a sample, okay, you don't have to worry about it. Okay, so is a third order, meaning that is K minus 3. Okay, this 3 stands for the third order, is the finite impulse response. Impulse is one of the input signals in electrical engineering. It is not the square, it's an impulse, is a very narrow width compared to square. And the equation is given by YK is equal to B1 U K minus 1 plus B2 U K minus 2 and B3 U K minus 3. With B1 equal to 1, B2 0.6 and B3 0.3. So suppose we're going to inject the system with the sinusoidal input. And this sinusoidal input is given by U is equal to sine 2 pi, okay, multiply 0.1 K which is equal to sine omega naught k. Okay, so this signal is injected to the system and applied to the system, so we have to derive the output. So very straightforward. So what you should do is UK here, you insert inside here, UK minus 1, UK minus 2, and UK minus 3 respectively. Okay. So under the input, the output is here, the equation is here, YK. The input is given, UK. So you just insert inside by applying YK, B1. So this one is UK minus 1, this is UK. So you make it UK minus 1. So you will get sine omega naught K minus sine. And same to the second part, UK minus 2, omega naught K minus 2 sine. And same to the K minus 3, omega naught K minus 3 sine. Okay. And psi is the phase of the system. So you simplify these equations, okay? You simplify this equation and it becomes yk b1 plus b2 over 2 cosine equal to sine plus b3 plus b2 over 2 cosine equal multiplied by sine omega naught minus 3 sine. And this equation is can be simplified due to the very complicated expressions by replacing the whole bunch in the bracket by B1 apostrophe and B3 apostrophe. Okay. So from there, so we have 3 parameter models. Okay. Manifest as a 2 parameter model when viewed through the lens of mono frequency input. Okay. So the system is 3 parameter model, but we can make it 2 parameter model. Okay. Using the manipulation of the sine and cosine trigonometry formula. But unfortunately, it is not possible to recover B1, B2, and B3 from a B1 prime and B3 prime. So we can rewrite the equations become like this. Okay, sine omega naught K minus sine omega naught K minus 2 sine, or we can replace as sine omega naught K minus 2 sine omega naught K minus 3 sine power of 3. Okay, so either one can do because we can manipulate the mathematical equations of the system and then we can estimate the parameters of B1, B2, and B3. So the further details you can refer to the example 2 in the book chapter 1, part 2. So I would like to drag your attentions to the one of the important issues in the system ID. Okay, we're still in chapter 1, which is the signal to noise ratio. Okay, so SNR is very important for the user, for the designer, for the student, research student. Okay, when they are doing the real, what do you call that? A real experiment to collect data. So the formula for SNR is given by variance of signals divided by variance of noise. Okay, is the relative contribution of deterministic excitations and random variations, quantified as a single formula SNR. So the term signal here refers to the true response. Okay, the true response that you get from the system, and having a good SNR is critical and very vital, okay, because it will affect the reliable parameter that we're going to estimate, and particularly the estimation method that we are going to apply. So it's very simple formula, whether is it high or low. Okay, since this is a ratio between the signal and noise, so the numerator, okay, the upper part must be high as possible, okay, and the lower part must be low as possible. So when you get 10 volt here on the signals, and then the noise is 1 volt, so 10 divided by 1, so the signals to noise ratio is 10, so it's considered is very good. But if you have a 10 volt signal here, and you have a 100 volt noise here, So 10 divided by 100, so it will become 0.01. So the signal to noise ratio is very low and considered it's not good, okay, because the noise is bigger than the signals. So we look at this example here, the effect of signal noise ratio on the parameter estimations. We have one output, output YK, and the input is UK, which is given by this linear equation. YK is equal to B1 UK plus B0. So it is Y is equal to MX plus C is a linear graph. Okay, so B0 is the intercept, Y is the output, which is on this axis, and U is the input, which is on this axis. So you have data which is plotted by X here. You can see that there is a lot of X. This X is the real data. Okay, and the signal noise ratio is 100. Okay, meaning that the ratio of SNR is 100. And when we find the curve fitting to fit all these data points, you can see that, okay, the equation become Y is equal to 5x, Y is equal to 5, X plus 1.989. Okay, so meaning that it is good. Okay, the curve fitting is good. And while you see the second one, okay, so the second one is the output, the SNR is equal to 10. And you can see that the data is a lot here, but the curve fitting here, the straight line here is given by Y is equal to 5.027x plus 1.965. So the fitting is not good compared to the left. Okay, this is based on the standard deviations. Okay, if you're using a statistic, standard deviation for the B1 and B0. B1 is here, the 5. Okay, B0 is the intercept. So you can see that the standard deviation is 0.036, 0.02, which is very small. But this one is 0.114 and 0.064, which is high. Okay, so from here you can see that the left graph is better, okay, because the SNR is 100 compared to the right one, where the signal noise ratio is 10. Okay, so the calculation here, where you have a signal to noise ratio, okay, sigma, the signal divided by the noise, okay. So we have two cases where SNR 100 and SNR 10 obtained from 200 samples of data. So the length of data is 200 samples, okay, which is plotted in figure 2.1 and 2.1a and 2.1b. So you can see a lot of cross there. This is a 200 data and 200 data. Okay. Oops, sorry. So in practice, SNR is not known as priori. So it's not things that you put in the, what do you call that, as a consideration, but it is important because it will affect your, the parameters value and the estimation method. Okay. However, several applications in the noise variance can be estimated from steady state data, and the input amplitude can be adjusted. okay, to the desired SNR. But SNR has a significant role to play in all estimation exercise, okay, because it quantifies the separate value between the signal and the noise. That is the first issue, which is the signal to noise ratio. So let's see the second issue in the system ID that always being discussed in the case study, okay, and in the conference and journal papers. This one is called as overfitting. Okay, so overfitting meaning that occurs when the model is trained to capture the local features of the data rather than the global characteristics. So it arises when one misconstrues the stochastic effect in the data as part of the deterministic input-output effects, where the change variation in the response are attributed to the change of input variables. It is like this. The easy way to understand overfitting is if the unknown model, okay, is a third order system, okay, but we fit the input and output data, then we get the estimated order of the system is equal to 6, meaning that we propose a model which is a power of 6 to fit the data which is already known as a third order system. So why we have an extra order of 3? It's supposed to be third order, but we fit as a 6th order. So this what we call as overfitting, okay? And the 6th order model that we get must be reduced, must be simplified and tested again, because it give a over order, okay? It's supposed to be 3, but we fit as a 6th order. So this what we call as a overfitting. Okay, this is due to the maybe some reduction in the bias, maybe comes from the standard errors of the model parameters and so on. So it is like this, okay? For example, you have a data here shown in figure 2.2. So this is the data, okay, that we get from the experiment, okay? So the input and the output. So we can see that is a polynomial, is it? Is a polynomial exponential. Fit can capture the relationship, okay, for this data. So in order to choose the appropriate order of the polynomial, so the sum squared error of the residual is drafted against the order of the polynomial as shown in figure 2.2b. So we find we are using the sum squared error. What is error? So error is the difference between the real value and the estimated value. Okay, so in this case, you can see that the first minimum point that make the system become flattened here is 3. So the good choice of the order is 3. Okay, it's not 2, it's not 4, it's not 5, it's not 6. Since the improvement in the residual norm at the higher order is flattened at after 3. Okay, so now we do the what do you call that the training. Okay, whether it is a third order or is it the fourth order or the fifth order. Okay, so what we will see is here. Okay, so you can see that the data, the third order that we estimate is here, which is similar to the data that we plot just now. And this is the fourth order, almost fit to the data, but it's not good as third order, and this is a fifth order. It fit, but after 5.5 is not converged to the value that similar to the data plot. So what we call here fifth order is the overfitting, fourth order is overfitting, and third order is the best data that fit this kind of data here, right? So the equations that fit the data okay, is a third order system. And this is the equations, okay, that we get using a least square. So I will not teach least square here, I just give you some equation because the least square method I will teach in chapter 4, okay, where y estimated k is equal to 1.183 is the first parameter, 0.384 is the second parameter, 0.314 is the third parameter, and 0.198 is the fourth parameter. Okay, and it is a third order system because it's a u power of 3. And you can see that plus minus 0.03, plus minus 0.07, plus minus 0.04, and 0.07 is the error, the tolerance error that we calculate for the parameter estimation here using the least square. Okay, so this is a overfitting is a important issues. So is a matter of to compare the estimated method, estimated model, and the true model. Okay, so you can choose the order and the coefficients that agrees well with the true ones. Okay, as long as you didn't overfit it. Okay, so we can see that the fourth and fifth order models is not suitable for the data given in the examples. Okay, so the reasons for the poor performance of higher order model is that they have to attempted to explain the chance variation using the input. You can see that the fifth order try to fit the data very well, but after somehow 5.5 input, so it didn't converge to the data that given in the examples. Okay, so this is the data, okay, the residuals, okay, that we obtain. So it starts from 25 at order 1, which is too big. Then it goes to 5 at second order, and then it goes to somehow 3 or 4 here, the residuals, okay, and then it start to flatten, okay, until 7. So the best order that we choose is the third order, okay, which give you these equations of the input and output model of the data given is the third order. So over parameterizations has to view not with reference to the true model, but with respect to the model that can be identifiable. The two reason of it, first, the process is usually much more complicated than the model that is being fit, okay? Therefore, we need a comparison of the model with the process with other method as well. And then secondly, the number of parameters and the order of the model that can be estimated is largely governed by the input excitations, okay? Which input you are using, either is a sine, either is a impulse, square, and so on. Okay, so far any questions? Any questions from in the class? Are you sleeping or are you boring and so on? Because we are in chapter 1, still a lot of theory. Everybody okay? Okay, everybody sleeping, very quiet. All right, so never mind. So we continue our lecture by looking at the samples here. So you are given a modeling examples, okay, how to apply journey of identifications from the beginning to the end. So you are given a schematic liquid level system here, okay. So what is Fi? Fi is the flow rate of the input. What is this? This is the control valve, okay. Is the control valve, is open and on, okay. And then the water will go into the tank, the single tank, okay. It's a single tank with the liquid inside, and there is another valve at the output, okay. So the output will go here at the rate of F naught. This is the output flow rate, and this is the input flow rate. So this is the input valve, and this is the output valve, right? And the height of the liquid level in the tank is represented by H. Okay. So from this diagram, okay, we totally know that this is a simple first order system. Okay, because it's a single tank. If the system is two tank or couple tank, so it is a second order system. Okay, this is what we call as prior knowledge. Right. So in this modeling example of liquid level system, we will see the physical process. We will see data generations. We will see data visualizations and preliminary analysis. We will see on how to build non-parametric models, and we will see how to build parametric models. With this, in this case, we are using the output error and the equation error. And then we are going to see how good is the model. We call it as the goodness of the models. We're going to see the predictions, deterministic tests, noise model tests, and so on. And then try to see other model beside transfer function, which is a state space model. So you can see here, this is the physical process, okay, of the interest. We have a buffer system shown in figure 2.4 here, okay. So F is the input flow rate, is a meter cubic per hour, okay. The unit is meter cubic per hour, and the output here is a meter cubic per hour as well at the output. So the objective is to build a model that explain changes in level H with respect to changes in inlet flow rate Fi. So the end use of this model could be in simulations, control, and monitoring of liquid level system. So how to generate data? So in order to generate data, we have two types. One is via experimental. The second one is by simulations. So first of all, we have to find the first principles model, which is by derivations. So for a single tank, the deterministic first principle model of the liquid level system based on conservation of mass is given by dH per dt, which is we differentiate the height of the liquid plus 1 over AC multiplied by CV square root HT equal to 1 over AC multiplied by Fi. Okay, with the assumptions. So we have assumptions. Incompressible fluid, number one. And number two is the outlet flow rate being proportional to the square root of the pressure head, which is the valve equation, is equal to F naught is equal to CV square root HT. So what is CV? CV is the valve coefficients. Okay, so every valve have their coefficients. So you have to look at the spec of the hardware. Okay, the valve coefficient of the outlet for CV, and the AC. AC is the area or the cross-section area of the cylindrical tank. Okay, so if you see the area, okay, let's see. Sorry, let me share. Okay, so this is the tank. Okay, so the area is here. This is the okay. So AC is equal to pi r square, the radius of the tank. Okay, so the water will enter here. Okay, and we will go here up. Okay, so you can see that this is the levels of the water. And the important one is the height. Okay, the height of the tank must be monitored. Okay. So the system is brought to a steady state before exciting it with the design input. So with the operating condition is set to Fi is equal to 4.5 cubic feet per minute, CV is 1.5, and AC is 0.5 feet square. So the nominal level is equal to 9 feet. You can see that CV here is the valve coefficients. Okay, so this one is we will get from the spec of the valve that we buy. Right, so that is the hardware, the process. Okay, so now is the input that we use for data generations. So the input that we're going to use is a discrete time pseudo-random binary sequence, or PRBS, which consists of a short and long durations, pulses switching between two levels around the nominal operating value. So the signals is shown here. Okay, so this is the PRBI signals. Okay, it's a square wave. Okay, but randomly generated. Okay, using a certain formula, which will be described in chapter 2 later. Okay, so this is the input profile. So you can see that the long durations pulse, which is a low frequency, secure the gain information, while not so long one is useful to capturing the dynamics of the process. Right, and then the output. Okay, the time, trends, and spectral flow of the level measurement. So we have an input, and then we have the output. So this is the output, and this is the input. Okay, you can see that the output try to follow the input as good as possible. Okay, and from here, this is a time domain. Okay, so when we apply frequency domain for PRBS, so the power spectrum density is like this. Okay, from 0 to 3 radian per sample. Okay, but for the output is shown here. Okay, where the maximum of the amplitude power is at 0. Okay, so power spectral density, the unit is decibel. Okay, and it versus the frequency, which is a radian per samples. So the response of the sample data, which is the equipment that we're going to sample, we call it as a ZOH. ZOH stands for zero order whole, or process sampler. Is obtained by numerically integrating the nonlinear ordinary differential equations, which is here. So we manipulate these equations, dH per dt plus 1 over A CV square root HT, 1 over AC Fi. So from time t to 2045 seconds, okay, by observing sampling times at 1 minute, okay. So this one is 2045 minutes, sorry, 2045 minutes. So the sampling is 1 minute, which is called as a sampling interval. So you apply this in the MATLAB Simulink, right, to input the data. And you can see that to make the system real in simulations, so we add some unpredictable noise, okay, to the system. So to render the simulation realistic, so a measurement error in the form of ideal, random, or unpredictable noise sequence is added to the true response with the SNR set value of 10. Okay. So we can see that the snapshot is here, similar to the figure that I shown before. Okay. So you can see that the input-output data is visually examined for the presence of any drift, outliers, and so on. So we can see here, there is no drifts for the equations. Drifts is equal to the age of the equipment that we use. If the equipment is too old, so this equipment might contribute for a drift data, which is must be removed, must be deleted from the data. And the outliers, is something similar like drift, okay, is the data taken is not logical, okay, it's out of the expected tolerance that we allow. So we must delete this data as well. So at the end of the day, we get this, okay. Okay, you can see that some pre-processing data is needed, okay, because this is the input and this is the output. So during the output, we added some random signals, predictable, unpredictable signals. So we need some pre-processing data. So from the data, you can see that steady state can be determined experimentally before introduce changes to the input, okay? Because such performance is we based on the alternative method, which is using the average reading as the nominal operating point, okay? So therefore, we can see that we apply a simple mean centering operations of the input and output data is used to generate the required deviation variables. So we come out with the equation like this: yk is equal to y estimate k minus y mean. Okay, so this symbol, the symbol above y at y and u is, we call it as the absolute value, real value. And the quantities under bar, which is here, this bar at y and u is a simple average of the respective variables, okay? Is the mean, is average. And then from the input and output data, we also can apply a spectral analysis. So to obtain a spectral analysis, we have a break for 10 minutes, okay? Is it okay we have a break, 10 minutes break?
Yes.
Yes.
10-minute breaks, please. We come back at 3:10.
Prof, can you share the slide
Yeah.
for 1A?
Okay, okay.
Thank you.
All right. Okay, hello. So 3:10. So we continue our lecture by looking at slide number 40. So it is useful to examine the frequency content of the output signals so that we can obtain the insights, okay, into the filtering nature of the process. So usually spectral plot, okay, power spectral density in decibel versus frequency, consisting of a graph, okay, is a 2D graph, power versus frequency on the x-axis, is widely used in this purpose. So high power in frequency band implies the strong presence of those frequency components, okay, as long as we can detect from the spectral analysis the strong amplitude, the higher amplitude shown there, significant frequency over there. So figure 2.5b here is examples. The top one is the spectral analysis for the output of the graph that we obtained in the previous lecture. Okay, and the second one is the power spectral density of the PRBS. Okay. Right. So you can see that the input and output spectral signals, where the power of the vertical axis is the measure of its strength. Okay, the y-axis over here. So it is useful to examine the frequency content of the output signal so that we can obtain the insight of the filtering nature. Okay, and then from there we can know what is the significant frequency, okay, that represented by the higher amplitude. So the liquid level system, okay, that's shown in the figure before, a single tank. The liquid level system is considered as a low pass filter, meaning that only any high frequency fluctuations in the input will be yield a poor response. So it only use the low frequency. Okay. So the output spectrum shown in the figure 2.5b show this point where you can see that all input components with frequency greater than 0.7 radian per sample have been significantly attenuated by the system. Okay, 0.7. Okay, you can see that after 0.7 is flattened. Okay, so it's a very low frequency between 0 and 0.6. So partition the data. So once you get the 200 samples of data, so we have to partition it. Okay, let's say you have a length of data 1,500 samples. Okay, the length of data you captured for the input and output of the single tank system. So from there, you have to divide into two. Okay, two sets. One is for the identification model. Okay, the first 1,500 for identification model, and the remaining 1,500 data is for the validation model. So that is the practice. So in this case, we have 300,000 data. The first 1,500 is for the identification model, to identify the model, and the remaining 1,500 will be applied in the validation model to validate that the model that we obtain is fit 90% above. So this one we will apply in chapter 5, okay, when during the case study. So both data are expressed in terms of deviation variables with the nominal operating point, okay, determined from the training data. Okay, so the following steps we are going to see how we partition the data. So from the system ID procedure, okay, can see that we begin with the model development with the estimation of elementary response of or non-parametric models, meaning that before we inject PRBS, we test first with the simple one directly from the signal generator, impulse signal, step response, sign, and so on. So what we do is, this is what we call as a non-parametric model testing. Okay, why we apply non-parametric model as the first step or the beginning of the experiment? Because we want to see some process characteristics. For example, did the system have a time delay? Did the system have a gain, DC gain? And is it the system have a time constant? Okay, so this is very important. Okay, so impulse response method, which using a cross correlation method, is the classical approach for delay estimation. Maybe can't see what is the time delay, so let me share with you what is the time delay. Okay, so time delay is something like this. So this is the output. Okay, this is the input, and you have the signals here. Okay, right, and this is the input. Sorry, this is not input, this is time. Okay, this is time. Okay, this is the input, and this is the output. Okay, so from here, you can see that there is a time delay here. Okay, here, a time delay. Okay, that must be included in the particular model, okay, of the system. And then the gain, okay, is the final change in the output to a unit change in the step input. So step response coefficient ideally is suited for estimating gain. Okay, the time delay we use impulse response, gain we use a step response, and then you want to see the time constants of the system, whether the system have a time constant or not. So this is referred to the 63% of the final value. Okay, so let's see if the system have a final value. Okay, okay, let's say this is a 1.1. So this is a 1.0. Okay, so 60%, 63% of the output, 1 is equal to 0.63. Okay, so 0.63 is somewhere here. Okay, 0.63. And this is what I call as the time constant of tau. Okay, of the single tank system. Okay. Right. Okay. Okay. So the response is naturally suited for estimating this parameter. Is we call it as the first test. Okay, first step before we inject the real test signals of PRBS to the system. Okay. So this is some impulse response estimations. Okay, we are using the formula here. YK is equal to summation of G multiplied by U Okay, U is the input, the impulse, G is the system. So we begin with L equal to 0 until M. Maybe it's 100 or 1000. Okay, by using a least square data, so we can collect the data and then we plot. Okay, so this is the sample of the impulse response plot. You can see that the impulse itself, the nature of the impulse signals is not like square. It looks like square, but the width is very narrow. So it can give you a real response based on the amplitude versus time. Okay, so you can see that the shaded region is treated as statistically insignificant. Okay, this is due to the discrete time have a unit sample delay. Okay, because single tank have a unit delay, which is expressed in terms of the samples. So physically there is a delay, no delay between the flow and level, but in the continuous time system as a zero delay. But in the sample data system, the presence of the delay is due to the zero or the whole of the sampler. Okay, so this decay or nature of the impulse response estimate a clear indication that the sample data system is stable, which agree very well to the knowledge of the process. So you can see that there is a point here, is a point. So this is the data that you captured using the analog to digital converter. And the distance between one point to another point is the time, sampling time. Okay, so if it is 0.1 second, so the next one will be, this is 0, 0.1, 0.2, 0.3, 0.4 until the end of the data. And then we can also use step response by using this formula. Okay, by mathematically relationships, it takes from the impulse response, but we modify. Okay, Y is the output, G is the system. Okay, so we inject the system, then we obtain the response that's similar to the drawing that I draw in the iPad. So you can see that this is a first order system because our tank is single tank. So it is a first order system, which is strongly suggests first order or an overdamp higher order if a second order is overdamp. Dynamic with a gain approximately 3.7 units. So if the system is approximated a first order process, so the time constant is about 7 samples. Okay, with 0.4, the steady state value is 4, 63% of 4, you can calculate that is about 7 around here. Okay, if I annotate here, it's about 7. Okay, somewhere here. Okay, this is the 63% of the output. Okay, which will give you the time constant about 7 samples. So how to build a parametric model? So parametric model will be discussed in detail in chapter 3 because it's very complicated. So I just give a little bit samples, the simple samples for you to digest because we are in the journey of identification in chapter 1. So it's use a difference equation, DE. Okay, it's not differential equation. Differential equation is using a S domain. Difference equation is using a discrete domain for the model deterministic process for the given data. Okay, so it's suitable for guessing the delay and the order of the differential equation form compared to the transfer function in continuous form. So we have an equation here, xk is equal to a1 xk minus 1, b1 uk minus 1. Okay, so this is what I call as observed through discrete time deterministic process. Okay, so if you don't understand it, don't worry because in chapter 3 we will go details. So we build the parametric models by estimating the theta, which is A1 and B1, which is unknown. Okay, estimated such that the sum squared one step ahead predictions error is minimized. So we take this data, and then we include here, and then we minimize it to obtain the equation of the prediction, okay, xk predictions, which is given by x hat. So however, this is only possible when the true response is known. If not known, it's not possible. So in reality, you must have the measurement of xk must be available. The data must be available. Therefore, the natural rewrite is a minimization of the term measurement prediction is given by minimum theta summations yk minus y hat. And then this estimate is bracket together and find the square, the error, the difference between the real and the estimated. Okay, so we can apply this in output error model and equation error model, which is the type of parametric model. So there are many parametric models, ARX, RMAX, okay, AR model, MA model, output error model, and equation error model, which will be described detailed in chapter 2. But for the readings, you can read the book chapter given in chapter 1, part 2. So after you get the parametric model, so we want to know whether the model is good or not. So this what we use a prediction error, okay, or namely known as a residual. So residual is the difference between the output, the real output y, and the estimated output y. Okay, y and y cat or y hat. Okay, this is the key quantity of interest in assessing the goodness of the models. So a good model should not leave behind residuals from that offer further scope for predictions while avoiding overfitting. So consequently, we can fulfill residuals cannot be explained by the input. Residual cannot be predicted using its own path, and the errors in parameters estimate are small or negligible relative to the estimate themselves. This is for the test for over parameterizations. That's why you can see here by looking at these two graphs in figure 2.8a, 2.8, we have a two graph. One is the output error model, is a parametric model number 1, and the number 2 is parametric model number 2 is equation error model. You can see that the data, okay, is represented by the x, okay, each of the graph, and this is the best straight line, first order straight line that represent the tank of the system. You can see that we find the correlations between the estimated and the real one. It gives you 94%. And using the other model, equation other model, we obtain 89%. So if in terms of without percentage, it is 0.94. Ideal is 1.0. 1.0 meaning that all the data, the cross data will be overlap the straight line that represent the best of the data. Okay, so this is 0.89. So of course, by looking at it, by observing it, this one output error model fit better, okay, with the correlation of 94% compared to the equation error model. Both are considered as a parametric model, but output error model give a better correlations, which is 0.94 or 94%. Okay, so this is the same thing that I discussed before. Okay, so the output error model far better than equation error model counterpart in the respect as evident from the correlation coefficients predictions, okay, between the y estimate and y real. So visualize is given here. So by looking at it, 0.94 or 94% is better than 89% or 0.89. And then for this system, we have a test for deterministic model. We call it as a correlating residual with input. It used the theory of autocorrelation and cross correlations, which I will describe in chapter 2, okay, maybe next week or next 2 weeks. So we want to see correlation, actually you want to see the relationship. Okay, we have a two type. One is autocorrelation. The second one is the cross correlation. So autocorrelation is we want to see the similarities, the signal with itself. Okay, compare with itself, meaning that we have input data, then we compare the input data with itself with time lagging. Okay, we shifted the data and see with the time lagging. While for the cross correlation, we have two data. Cross correlation must have two data. Okay, if you have no single data, we cannot perform cross correlation. You have a single data, we can perform auto correlation. You have more than two data, we can perform cross correlation, because cross correlation involve two different data. So we compare between data 1 and data 2, or input data and output data, then we compare shifted to the time lagging and see what happened in the graph. So this is the cross correlation between the residuals and the lag inputs. You can see that the residuals and the lag input here, okay, give a accepted correlation, which is below 0.05 at the tolerance. The tolerance is represented by the dotted line. Okay, so the dotted line, the tolerance is very small, meaning that the correlation is accepted between the residuals and the lagged inputs. So significant correlations between EK, which is the difference between input and the difference between the real and estimated output, and input UK at positive lag directly implies that the effect of input of the process response have not been completely explained. Okay, so that's why figure 2.9 clear that there exists no significant correlation between residuals on the OE models and the inputs at any lag, so it satisfactorily captured the dynamics of deterministic process due to the small value. So on the other hand, the residual from the other models, for example, ARX model, are significantly correlated with the inputs, implying that it has not managed to adequately capture the deterministic effect. So the ARX model, auto-regressive exogenous input, also will be described in chapter 3 later. And as I told you before, the autocorrelation for single data, correlation is for two data. So we capture the data between the residuals and input for these models. You can see that the value is beyond in the tolerance, very small tolerance. Okay, similarly to the correlation between the residuals and the lagged inputs. And then based on this, we estimate the parameters. So since it is we have parameter estimate errors for the best equation error model for the liquid level system. So we estimate A1, A2, A3, A4, and A5 at this value, okay, which is for A and B, okay. And this value is accepted due to the new very small percentage error at the bracket value, right? So this is clearly, okay, the output error model is clearly the best choice compared to the equation error model, okay, for the parameter estimation error, which is very small, and parsimony. Parsimony meaning that is a very minimum parameter which really represent the accuracy of the model. So it have a very optimum and very minimum parameter values. And then we try for the test for noise models. This is predictability in residuals. So you can see that the error, also the autocorrelations, okay, of the residuals from the OE model is also small, okay. So it is accepted for this kind of correlations, okay. And then the cross validations. So is a good model is one which yield good predictions on the fresh data sets, okay. So this is the predictions of the output error model for the test data, okay, you can see that. and then the observations and the predictions of the output is shown here. So you can see that this is what we will get during the case study, okay, in chapter 5. So you are required to plot the real and the simulated, or the measurement or the simulations, okay. So the cross line is the predictions and the observed is here, okay, which is considered for the output error model accepted, but can be further improved, okay. So cross validation is important for the validation steps where you apply a normalized root mean square, NRMS. And the formula is given here, RF is equal to 1 minus double modulus between the actual Y and the estimated Y. Okay, so where Y and Y cap are the measurement and the predictions. Okay, and Y bar is the mean value of Y. The notation of the double, okay, the double modulus 2 stands for the 2 norm of the vector. And this prediction calculate about 72% fitting, okay, which shown in the figure 2.21b. This one is 72%, but can be further improved. That's why I told you, can be further improved due to the fact that in order to fit the data and the solid line, a minimum percentage is 90% and above. Okay, so but we gain 72%, but this one can be further improved using other parametric model. And at last, we obtain the final model. So this final model, okay, assessed given by yk output equal to xk input plus ek. Ek is the stochastic part, or the uncertainties, or the noise, or the disturbance, and which is represented by minus A1 cap and B1 cap, okay, xk minus 1, because this is the first order system, and we estimate A is equal to minus 0.88 and B1 is equal to 0.4621. Okay, so it is also a common practice to express this difference equation in what is known as a transfer function operator form. Okay, so in transfer function operator form, you can write as here, okay, 0.4621 Q minus 1. Q minus 1 is equal to Z minus 1. So some books is using Q, some books is using Z. So this is the model, the mathematical model of the single tank, which is in our study before. Okay, we are looking at the how to obtain the journey. So the journey ended here at the final model. It started with the schematic single tank. Then we put some what do you call that, input impulse, input step, then the parametric model. There's a non-parametric model. Then we analyze it, and at the end of the day, this is the final model that represent the single tank process control system. Okay, so to obtain this, this one is more in chapter 4. Okay, where we have to use the least square estimate, we have to use the prediction error method and other method in order to estimate this parameter value of A1 and B1. Okay, any questions so far from the floor? Before we go to the chapter 1B, the last one for today. Any questions? No questions? So if no question, we go to the chapter 1B, the final one. Okay, a very short one. Okay, so in chapter 1B is the mathematical descriptions of the process models, right? So as I told you before, a model is a set of linear or non-linear, ordinary or partially differential or difference equations, algebraic equations in terms of the process variables, states, inputs, and parameters built on set of assumptions. So in terminology, modeling is literature inputs to a model need not correspond to the physical inputs to a system. So similarly, output needs not correspond to the physical output as well. So they have a broader connotations. So the output of the model constitutes of those variables that we wish to predict or explain, while the inputs to a model include all those variables that participate in their predictions. So further known as explanatory variables. So if you can see here, the A is the process to generate the outputs. The B is the model predicts output. So the difference between this process and model, process is the real experiment, okay? But model is a simulation of the mathematical descriptions, okay? So both are more or less is it looks like similar, but actually in the reality is different. Okay, so in the process, we have the inputs, which is the adjustable variables. We have the stochastic effect, which is the disturbance, the noise, okay? And then we have the output, which is the measured variables. But in the simulations, we have the models here. We inject the system, which is the explanatory variables, which is the regressor. And then there is the input for system parameters of physical properties. And there is the output, which is the predicted variables. That's why all these predicted variables is very kept. So in highlight to that, model input is the broader set compared to the process, okay? So it consists of the past and the present inputs to the process and all other variables that participate in the predictions of the output interest, okay? So important part of the model is you cannot forget the set of underlying assumptions. There must be assumptions. If there is no assumptions, our experiment will be difficult, okay, to accept the data. So a popular class of a description known as a state space model used in additional to set of variable known as a state to describe the process. That is considered as the another part of the model, which known as a state space model, which consists of matrix A, input matrix, matrix B, system matrix, matrix C, output matrix, and matrix D, which is the feed-forward matrix. So that's why, in order to classify the model, we may ask such several questions. So, do we wish the model to the steady-state behavior of the transient dynamic behavior? Is it the process variable depend on the process directions other than time? So that is the issue of the question that we must ask. Then, does the process of the interest possess purely random behavior? What kind of input and output relation that we have and desirable? What is the use of the end of the model? Okay, do you use for the control? Do you use for the monitoring, optimization of predictions? Or should the model physically meaningful for interpretable, where the structure of the model required to follow a form from the prior knowledge, okay? That's why these issues must be clearly been defined, okay? That's why I give this figure, okay? So the definition and details of each type of the models, okay? First is the first principles and empirical. First is derivations and experiment. Whether the model is a linear or non-linear. Whether the model is time varying or time invariant, okay? Time invariant is the model is varying with time, and this one is output is follow the input for the time varying. Deterministic or stochastic. Deterministic is only on the process part, but stochastic is the uncertainties that enter to the process and to the output, plus the input of the system. And whether the system is a single scale or multi-scale. The one that I show, the single tank, is a single scale, a simple one. But in the reality of the process, we have a lot of tanks. A single tank, a couple tank, a triple tank, and so on. So that considered as a multi-scale. Continuous or discrete. So whether you are using a Laplace transform or Z transform, whether you are using a static model or dynamic model. So static model usually refer to the process control. Okay, you can see that the tank is not moving. There is no tire for the tank. So the tank is static over there in the lab. But dynamics is involved in the motor, AC motor, DC motor, generator, and so on. This is all is the dynamic system, including a suspension system. Whether this is a lump or distributed, some of the system is lumped together. Okay, all the subsection is lumped together compared to the distributed where we cluster into the simple one. So that one you call is a distributed model. So that's why can be classified as an approach to modeling. Approach to modeling is first principle versus empirical, or system characteristic. This is involved linear and non-linear, time varying or time varying. Or it will be classified as a knowledgeable available to the user, which is deterministic or stochastic, whether it's a black box, a gray box, or white box. Or is it a domain of modeling, which is a continuous and discrete time, or time or frequency domain. Or either is a response characteristic, which is a static, dynamic, or lump or distributed. Okay, so that's why, as I told you before in the chapter 1, so there is the advantage using first principles and empirical models. Both can be used, both can be applied, both have a pro, both have a con. Okay, so both will do. Okay, in other words, naturally, both can do. And usually for the empirical models, we focus on 4 main things, whether it's a non-parametric or parametric way. Okay, non-parametrics is usually using impulse response, using a step response, using a frequency response, and power spectrum density. A lot of graphical information from there. But parametrics is not using graphical representations. It's using a lot of mathematics and difference equations. Okay. Compared to the empirical model as well, we have a black box and gray box. So black box is no prior knowledge at all, zero knowledge, but gray box you have about 50% or 70% of the knowledge. That's why in order to obtain a composite of the model from the identification can be roughly a drawing by using this block diagram, okay, where you have a deterministic model over here. You have all the system, you have the input, and then you have the stochastic part. So this is the important part. If you want your model to be as simple, you can ignore this stochastic part. Assume it as a 0. But this is but when the noise or disturbance is higher, so you must include this stochastic part. So this is a non-linear part of the system. That's why the process response observed is very important. Okay, so I conclude my lecture today. It's important advantage of choosing the linear time invariant system descriptions. Okay, to a large class of stochastic effects can also be modeled. A response of the LTI, linear time invariant system driven by fictitious random signals. So this will conclude our chapter 1. So I wrap again. So I give you 3 slides, chapter 1, chapter 1A, and chapter 1B. And book chapter, chapter 1, part 1, chapter 1, part 2, and chapter 1, part 3. So this is all the materials that I use, including my slide for the chapter 1, system ID, introduction, and some journey and some model specifications. So I hope the materials that I give to you will help you, okay, in order to understand for chapter 4 lecture. Okay, with this I end my lecture today. Is 3:49 now. Any questions before we end the session?
No, Prof.
Okay. So with that, I end my lecture. If you have any question, you can WhatsApp direct to me. Thank you very much.
Okay.
See you next week.
Okay, thank you. Thank you, Prof. Thank you.